So our topic for today is Gauss's law in electricity, in electrostatics, specifically in electrostatics. You'll find Gauss's law in almost all the branches of physics. What is Gauss's law in electrostatics? Let's understand it. I have explained to you what electric flux is. In my earlier videos, I have explained what is the meaning of electric flux. Just for a recap, let's say these are the field lines, electric field lines, or also called lines of force. These are electric field lines, E. This is E. And we have a surface. The surface is like this. Let's say this is the surface. This is a surface. Okay. Now, if we draw a normal to the surface, it will be like this, that is perpendicular to the plane of the surface, and let this angle be theta. So this is E, this is theta. Total electric field lines crossing through this surface, see, crossing through this surface, normal to the plane of the surface, will be E. I'm using the magnitude only, E. If the area of this surface is A, then A and then cos theta, this is E cos theta. Okay, this is flux. This is called flux, electric flux, that is passing through the surface. So from here you can understand that in vector form this will be E dot A. Clear? So now when you know what electric flux is, let's understand what is Gauss's law. Gauss's law says that the total electric flux through a closed area, the area is closed here. We are talking of closed area. Here what I had drawn, it wasn't a closed area, but what is a closed area? Let's say these are the electric fields and this is a closed surface. And the area of this closed surface is A. So Gauss's law is applicable to closed surfaces only. So it says total electric flux through a closed area. You know, E dot A is flux. When it is a closed area, this will be line integral. This means closed integral. So E dot A, total electric flux through a closed surface, is equal to the total charge. Let's say the total charge enclosed by this closed area is Q by epsilon 0. That is the permittivity of the space. This is Gauss's law. Let's understand. Let's say you have Q1, Q2, Q3. There are three charges inside a closed surface, that is, let's say, a sphere of radius r. Now, according to Gauss's law, it says that the electric field into area of this, what will be electric field? Let's say E. We have to find what is E. So E in dot A. What is A? Complete A. You know, for a sphere, total area is 4 pi r square. This will be equal to the total charge enclosed inside this surface. Total charge enclosed is Q1 plus Q2 plus Q3. So it is Q1 plus Q2 plus Q3 by epsilon 0. Simple. This is the meaning of this. So from Gauss's law, you can find what electric field is. The magnitude will be, let's say, I write like this, summation Q, that is all the charges enclosed, by 4 pi r0 epsilon 0. Okay. And what will be the direction? It will be radially, if these are positive charges, so radially outward to this. So you can find the direction also. This is the meaning of Gauss's law. It is a very useful law to find the electric field, and all the other variables, all the other potential and all, whatever variables are dependent on electric field or they have some relation to electric field, you can find it. First of all, you will find the electric field and then you can find the other variables. Clear? So let's start with simple examples. Line of charge. I have in my earlier videos, I have deduced the formula of electric field because of long line of wire with charge Q or linear charge density lambda. I have found the electric field due to a ring, or if this is a sphere, spherical shell, or a complete sphere, solid sphere. So I have deduced the formula or expression for electric field because of these shapes by using the very fundamental method of integrating through the complete symmetry of the shape. Now we'll see how Gauss's law can be used to find the same and how it is easier than the fundamental method. So let's start with a long wire. Okay, you can do one thing. You can say Q charges over the whole wire, or you can say the length is length is L and lambda is the linear charge density. Then lambda will be Q by L, not lambda by L. So this is linear charge density, this is length, this is charge. So whatever suits you, you can use it. We have to find what is the electric field at a distance r. We have seen how to, in our earlier videos, what we did. We took a small element here, then we saw what is the electric field at this point. The y components were cancelling each other, so we had only x component, and then we integrated it from here to here in terms of theta from minus pi by 2 to pi by 2. Now, very simple way. What we do using Gauss's law, we find the Gaussian surface. What is Gaussian surface? Gaussian surface is that closed surface. So let's say we have a cylinder that inside which this long wire is situated. Okay, this is an imaginary shape. It is an imaginary shape that is called Gaussian surface, just to find out the electric field because of this wire. So we have to find at this distance r. Okay, you have to find what is the electric field at this point. So what we'll do, using Gauss's law, we know, let the electric field intensity be E. I'm not using arrow and then taking the magnitude. This means the magnitude of the electric field. So E into the area of the Gaussian surface equal to the total charge enclosed. Let's say the total charge is Q. This is epsilon 0. Okay, according to Gauss's law, this is what we will get. Now let's see, what is A? What is the area of this cylinder, this surface, not this and this? You know, it is, if the radius is r, 2 pi r into L, the complete length. This is area. What is Q? If lambda is the linear charge density, then lambda into L is Q. So we will put it in this equation. That is E into 2 pi r L is equal to, we just saw it was lambda into L by epsilon 0. That is electric field intensity at a point, let's say P, which is r distant from the wire, is given as L cancels. So what you have is lambda by 2 pi epsilon 0 r. This is your expression. And what will be the direction? If the charge is positive, it will be radially outward, and if the charge is negative, it will be radially inward. That is, if the charge is positive, it is like this, and if the charge is negative, it will be to this side. So you see how easier it is to use Gauss's law to find the electric field intensity because of a shape. So when I have explained this to you, now let's understand a few things about flux. This was necessary so that you understand what we are talking about, what is the use of this theory. We have considered the fact that our flux is constant. If the flux was varying, we couldn't have used this. Second is, it is useful only when the Gaussian surface taken is symmetrical. Symmetrical in the sense, what I mean to say, that the charge, the body that carries the charge, has some symmetry. What is the meaning of it? See, if we take point charges, or if you have any wire, or you have cylinder carrying charge, or you have a sphere, so you can enclose them within spheres, or you can enclose them within cylinders, so that you have a known area. For example, we used A equal to 2 pi RL. If this is not the case, if there is no symmetry, one charge is here, the other charge is somewhere here, and you have to find electric field here. So that becomes very difficult. So there has to be some symmetry to it. This you should keep in mind. Now, electric flux is additive. If you have, let's say, 3 charges, Q1, Q2, Q3, and there are electric field lines due to these charges, and you want to see what is the charge at this point, which is the center, which is r distance from the center. If we take it, let's say this is a sphere, then what I mean to say, the flux out of this combination of charges, if that is phi, is actually equal to phi 1 plus phi 2 plus phi 3. That is electric field due to 1 plus electric field due to 2, electric field due to 3 into area. So this is additive. Flux is additive. This you should keep in mind. We'll use it when we'll have to find electric field intensity because of some shape which can be where we can have assumption of a symmetry. For example, if this is a disk and inside this disk another disk is cut out, so we have this shape only, and we have to find electric field due to charge on this shape. Then we'll have phi, let's say phi 1 because of this and phi 2 because of this. The net flux will be, since this has been cut out, it will be phi 1 minus phi 2. So this is why I told you why this property is important. It is an important property of flux. Now let's see electric field intensity due to an infinite sheet of charge. We have seen it. What it will be? Let's say this is the infinite sheet of charge. Charge is onto this side. Let the total charge be Q. Okay. So if total charge is Q, we know this sigma. This will be equal to Q by what? A. So this is what? Surface charge density. Now we have to find electric field intensity at certain point. Let's say r distant from this sheet. What it will be? The area will be, see. So we have one area to this side and one area to this side for electric field. Plane area A. So E into A, this you know. So this will be 2A. If area of one side is A, then area of the other side is also A. This is a sheet, it has some area. So one area is to this side and one area is to this side. So E into 2A. This will be equal to the total charge enclosed, that is Q, which you can write as sigma into A, Q by epsilon 0. Okay, this is from Gauss's law. So A cancels A, finally E is equal to sigma by 2 epsilon 0. We had seen when we had deduced the expression for electric field using fundamental method of integration. We had seen that for small distance from the sheet, it becomes independent of the distance of the point from the sheet. That is, whether it is at this point or it is at this point, it is immaterial. When the size of the sheet is very large in comparison to these distances, small distances. So this is the case. If Q is positive, it is in this direction. If Q is negative, it is in this direction. Okay, so this is electric field intensity at a point away from an infinite sheet because of a surface charge density sigma. Okay, then let's see third one. Let's talk of a spherical shell. This is a shell, that is inside it is hollow. So let's say the radius is r, capital R, and we have to find electric field intensity at this small r. The total charge on this sphere is Q. So what we do? We take E, that is, this R is greater than R. The case is that R is greater than R or equal to R. That is, the point is outside this sphere. The point is outside this sphere or on this sphere. Then what? See, this will be E into area. Area of the sphere is equal to total charge enclosed. It is Q by epsilon 0. In the start only I told you, the whole sphere carries this charge Q. It is spread over that sphere. It is a ball. Let's suppose it's a ball. So Q is spread over this ball, and we are taking a point that is out of the ball. So this is the first case. So this is this. What is area of a sphere? Obviously this is 4 pi r square, we are using this. So the Gaussian surface is what? We take area of the Gaussian surface, don't think we take area of this. So this is also a sphere. The Gaussian surface is also a sphere that encloses this small ball. So it is 4 pi r square, which is equal to q by epsilon 0. Now if you rearrange, you get 1 by 4 pi epsilon 0 q by r square. Now if you look at this expression carefully, it simply reflects that you are taking the electric field intensity due to a point charge at this point. That is a point charge of q, and you have to find electric field intensity r distant away from it. This expression is equivalent to that. Okay. Now second case, when r is less than r, that is we are talking of some point inside this sphere, not a sphere, spherical shell. Let's say our point is this. So our Gaussian surface will be this sphere. Okay. So this will be E dot 4 pi r square. The area of the Gaussian surface is this. This will be equal to q by epsilon 0. But do we have any charge inside it? This is hollow. Charge is spread on the surface of the sphere ball. Inside this, the charge is 0. So this is 0 by epsilon 0. That is 0. So electric field inside it is 0. Okay. Now let's see what if this is a solid sphere. Now what if this is a solid sphere? It is a solid sphere and the charge is q spread across this sphere. It is volume charge density. So if it is volume charge density and the radius is r, let's say capital R, then you know the volume of this sphere will be 4 by 3 pi r cube. This you know. So your volume charge density, that is represented normally by rho, is given by charge by volume. Okay. So you have rho equal to q by v. Now if we take a point r that is out of this sphere, that is case 1, when your this is greater than or equal to capital R, then what? Your E dot area of the Gaussian surface. Gaussian surface will be this sphere. So E dot A is equal to q, the total charge. Charge is q by epsilon 0. What is this? This is area is 4 pi r square, that is E dot 4 pi r square small q by epsilon 0. So from here you see it is again equivalent to a point charge at the center of this sphere. So it is like we have a point charge q here and we are taking electric field intensity at distant r. So you understand this? You can have many different formulations. If you put the value of q here from this, so q is basically rho into v. Okay. So that this is 4 by 3 pi r cube. This is v into q. Sorry, not q, into rho. If we are given with volume charge density. So 4 by 3 pi r cube rho. So from here you can cancel 4 pi. What you get is E will be, see here, this is this by epsilon 0. Q is this, so epsilon 0. So what we get? We get r cube rho r square epsilon 0. So you get this expression. So whatever you have, you can put your mind into it and find the result. Okay. Now let's say our point is inside it. This is our point. That is, this is r, small r. So what we'll do, we'll take a Gaussian surface here. Then what? This is the case number 2. That is r less than r. Then E into area of this Gaussian surface. Again it will be 4 pi r square. And q, let's say the new q is q dash. That is q because of this sphere only. We have this q spread across this volume. But what is the charge contained inside this sphere of radius r? So that is q dash by epsilon 0. Now let's see. Our volume charge density is this. Therefore, Q dash will be 4 by 3 pi r cube. This is the volume of this sphere into rho. So you can use it here, or if you want to, you can find, you can put the value of, see, you have rho. So rho is Q by V. So you can put it like this, 4 by 3 pi r cube into rho. Rho is Q by this 4 by 3 pi r cube. So this cancels this. What you get is, it is Q r cube by r cube. So Q dash, you can put this also, that is Q r cube by epsilon 0 r cube, and when you take the value, it is E is, here you will get 1 by 4 pi epsilon 0 from here and 4 pi from here, and r square cancels this, so you have Q r by r cube. This is the expression for the magnitude of the electric field, and you know if the charge is positive, it is radially outward, and if the charge is negative, it is radially inward. So I think you have got the concept. Okay, so you know outside the sphere the electric field intensity is as if we had a point charge at the center. So let's find out if we have this sphere, okay, and we have a small sphere of this cut. Let's say this is the center, the radius is capital R. You can coincide it also, or you can simply, let's simply use it. Let's say it's not r by 2, but let's say the radius is small r. Now if we have to find electric field intensity at a point P, which is, let's say, x distance from the center of the larger sphere, what will be the electric field? See, we can think of these as two separate spheres. Electric field due to this will be, E1 will be 1 by 4 pi epsilon 0 if the total charge on, now the issue is what will be the charge on this. So let's say the charge on this portion is Q1, so it is Q1 by x square, okay, and E2 because of this will be, this is x and this is r, so we'll have E2 equal to 1 by 4 pi epsilon 0. Let's say the charge on this sphere is Q2 and this will be x minus r. Okay, this is simple, and we'll add the two. Add the two means this is gone, so this minus this will be the electric field at this point. Now what is Q1 and Q2? That is important. We say that Q is in this part, Q, or we can say, let's say Q was on the complete sphere. Then what? See, if Q was on complete sphere, then the volume density, volume charge density will be Q by V, that is 4 by 3 pi r cube. This is rho. So Q2, this one, this will be, Q2 will be rho into its volume. And what is its volume? Its volume is 4 by 3 pi r cube. So we know what Q2 is. Complete Q, this would be rho into 4 by 3, that we have written it here. Therefore Q2 will be Q minus Q2. Q2 you know, sorry. Therefore Q1, if this is Q1, so Q1 will be Q minus Q2. So you get it? It is 4 by 3 pi rho r cube minus r cube, capital R cube minus small r cube, that is 4 by 3 pi rho r cube minus r cube. So this is the charge on this surface. So we know what is Q1, we know what is Q2. We can put these values and find the net electric field intensity at this point. This will be what? It will be E1 minus E2. Okay, and obviously if it is positive charge, it will be radially outward of it, and if it is a negative charge, it will be radially inward. So I think I have given you enough concept how to use Gauss's law to find the electric field intensity because of several or different shapes. Now you can go to the book and try solving examples. You'll understand it.